Uh, so this term, analysis of variance, was introduced by Professor Ronald A. Fisher, who was our father of modern statistics. He was dealing with some kind of agronomical data. Then he developed this particular technique. And this technique is one of the most powerful statistical tools to test the significance difference between not two sample, but more than two sample, okay? Whenever we came across certain kind of data where we have more than two sample, then we have to go for this analysis of variance technique. By using this technique, we can observe the significance difference between the samples, okay? Till now, in your course, we have been discussing this test of significance of t-test, as well as for large sample, we have been discussing capital Z test, and even chi-square test that is valid for both large as well as small sample. But this analysis of variance is also one of the test of significance tool only. It's a powerful tool to consider the sample which are more than two. From these samples, we can observe the significance difference among them, okay? In this particular slide, it has been said that the analysis of variance is a powerful statistical tool for test of significance. The test of significance based on t-distribution is an adequate procedure for testing the significance difference of the difference between two sample mean. In a situation where when we have three or more samples to consider at a time, an alternative procedure is needed for testing the hypothesis that all the samples are drawn from the same population. That is, they have the same mean, okay? So analysis of variance also, no doubt the technique name is variance, but here we are testing mean only. Till now in test of significance, between difference between two sample mean, or we can say difference between population mean and sample mean. So all these tests of significance, here we are testing the expected value and the difference between the observed value, okay? So we are moving towards our next slide. This example we can consider. This is the example of fertilizers. Here we can compare the fertilizers, four different fertilizers if we consider that is used in agricultural field, and that are applied to certain kind of plot of crop. Then how the yield of that crop will give while applying all these four fertilizers are different because their quality of the fertilizers will be different. So how we can observe this, how much they are significantly different or they are same by the technique of this. By analysis of variance, we can observe the fertilizers, their significance difference or not, okay? So how this variation is calculated? In mostly the Anova, we consider two types of variation, assignable causes and chance causes. Assignable causes are the causes which can be controlled by human. It is in our hand to reduce them, or they can be traced also, but chance causes are not like that. Chance causes are inevitable. They cannot be controlled as well as they cannot be identified, okay? So whenever we have to observe the variation between the samples, first sample is different from second sample is different from third sample, like this way, we have to consider two types of variations: assignable causes, the variation that is coming from assignable causes, and the variation that is coming from chance causes. So in this particular slide, it has been said that variation due to assignable causes can be detected and measured, whereas variation due to chance causes is beyond the control of human hand and cannot be traced separately, okay? In the coming slides, we will be considering one or two examples that it will be more clear to us. And we all know variation is inherent in nature. Any, not only for this analysis of variance, any data that we came across in statistical data, it has certain kind of variation, and variation could be measured. Some kind of variation could be measured from measure of dispersion techniques also, how much they are scattered or how much they are clustered around the mean, or some kind of other measure of central tendency, okay? So variation is there only. Variation is inherent in nature. So for the validity of this particular Anova test, we have to follow certain kind of assumptions. There are three main assumptions regarding this Anova test. And here we are taking help of the F-test statistic. F-test statistic was developed by some person which follows distribution, F distribution, Snedeker's F distribution. And we all know our steps that we have followed in test of significance, that we need to take help of a test statistic to observe the difference between the expected value and observed value. So here also we are taking help of this particular test statistic, F-test statistic. and certain kind of assumptions should be fulfilled. If they are not fulfilled, that we cannot go for this particular ANOVA test. Okay, so first assumption is the observations are independent, and the second assumption is parent population from which observations are taken is normal. Normal population from which we will be taking one sample. All this calculation regarding ANOVA will be based on sample only. We are not considering whole population. Okay. And the third assumption is that various treatment and environmental effect are additive in nature. Okay, this is also one of the most important assumptions. So these are three main assumptions of ANOVA. We have two types of ANOVA. There is one-way ANOVA and two-way ANOVA. Okay, so first we will be discussing about one-way ANOVA, with certain kinds of problems will be there in the slide, and then we will move towards our two-way ANOVA. One-way ANOVA, when we say one-way ANOVA, it's a technique to observe the significance difference between the samples, okay, and how these observations are classified on the basis of one factor only. That's why its name is one-way classification. On the basis of one factors only, certain numbers of groups or certain numbers of samples, it will be classified into a finite number of classes, okay, and each sample will be covered with certain kind of sample size. Okay. That's why this slide has said that let us suppose that capital N observation, we have y11, y12, y13 like this way of a random variable capital Y are grouped or on some basis, on some factors, into k classes of sizes. Okay, so this k classes of sizes having some kind of sample size, like first class will be having a sample size small n1, second class will be having sample size small n2 like this way, and kth class will be having sample size small and suffix k respectively. So from this table also we can observe how the one-way classification has been done. First class contained the observations like y11, y12, yn1, okay, and its total is t1 dot. This is some kind of notations that has been used in ANOVA, and the total of the observation divided by sum of the observation, that will give us our first class sample mean. We'll be saying this as first sample mean, that is y bar 1 dot. Similarly, we'll be calculating other sample mean also for second class or second sample, for third class or third sample like this way, kth mean. Okay, so what we are testing here in ANOVA, we are testing this significance difference among this mean, that y1 bar dot is different from y2 bar, or y2 bar dot is different from y3 bar. If it was for two sample, that we shouldn't have adopted this particular technique, ANOVA technique. We have adopted certain kind of t-test or some kind of z-test, okay, for two sample mean. But here, since it is a more than two sample, kth sample, say k is a finite number, say 10. So 10 sample mean or karne ami jodi if we consider we have to observe the significance difference among them, then we have to follow this particular technique, ANOVA. How the difference is coming in ANOVA, the first sample is different from the second sample, is considering the variation between the classes and within the classes. Okay, between the classes in the sense that first class will be different from the second class will be different from the third class. Like this way, it is between the classes. The observations as well as the sample sizes will be different between the classes, and within the classes in the sense that the observation within the class, y11 will be different from y12, y13 will be different from y14. So within the first sample, within the second sample also there is some kind of difference is there, variation is there, and between the classes also there is some kind of variation. So in ANOVA, to get a real significant difference between the sample mean, we have to consider two types of variation, that is between the classes and within the classes. So that's why it has said that the first type of variation, the between the classes variation, is due to the assignable causes, okay, which can be detected and controlled by human involvement, that I have already mentioned. And second type of variation is due to chance causes, which are beyond the control of human hand. So within the classes, we cannot, within the classes, the variation that is coming from the observation, we cannot control them, okay. But between the classes, the variation we can be that can be controlled as well as reduced, okay. So I hope everybody is understanding till now. So here we are considering one particular example related to how we are applying here analysis of variance technique. So this example consists of capital N number of cows. We can consider capital N as a finite number, say 100 cows. 100 cows has been divided into some kind of, on the basis of some kind of ration that has been fed. The ration that will be fed will decide the output of the yield that the cow will be producing. So K defined ration, on K defined groups, the 100 cows has been divided. So if we consider K as 10 defined ration has been applied to this 100 number of cows, then each, if we consider 10, 10, 10, so 10 number of classes or small k will be considered here. Okay, so this 10 different sample, the mean yield of the milk, the variation that has been considered from this ration will be considered, as well as the error within the variation, within the observation, means the we all know that no two cow produce the same amount of yield of milk. So within the cows also there will be variation, and the yield of milk will be influenced or affected by the different types of ration that has been applied to the cows. Okay, so in one way ANOVA, on the basis of certain kind of one factor only, the observations are divided and the variation will be considered. So let us consider the effect of K different rations on the yield in milk of capital N cows, and here breed and stock has been put constant. So cows has been considered same breed and same stock. So first Roman 1, that is the effect of the ration, we can say it as a treatment, and the second is error produced by numerous causes of such magnitude that they are detected and identified. So this is the mathematical model we'll be using in one way ANOVA. That is, in the left hand side, that is the yield of the milk fed by the J8 cow while giving the I8 ration. Okay, and in the left right hand side we have mu, that is the general mean effect. This effect will always be there because we all know the yield of milk of two different cows will be not be same. So either we are giving the ration, proper amount of ration, or we are not giving the proper amount of ration, their difference will be there between the yield of milk produced by two different cows or say 10 different cows. Okay, so mu is the general mean effect and it's a fixed effect. It will be always be there. And epsilon ij, that is the effect due to chance, that we cannot control. It is not in our human hand because the cows may be having some kind of health related problem or some kind of genetic problem, so they are not producing the adequate amount of yield. How much improved ration we are applying to them, but they are not producing adequate amount of yield of milk. So this effect is due to chance in between the cows. Okay, that cannot be controlled or cannot be traced and identified. So how this we'll be needing some kind of quantitative figure. Till now we have known that here two types of variation will be considered: variation within and variation between. Variation within and variation between will be considered. Till now we have considered, but we'll be needing some kind of quantitative figure. So mean square has been considered. Two types of mean square will be calculated in this particular ANOVA technique. One mean square is due to the variance that has been occurred due to within classes, and two second mean square will be calculated for variation that has been occurred between the classes. So if we see nicely, then we can say that the mean square formula here it has been given as sum of squared deviation from mean divided by degrees of freedom. This is we can say it is a sample variance also. Thus it is similar to sample variance formula. And we all know population variance is denoted as sigma square, which is the formula for grouped as well as ungrouped data. We have came across this. So here also between the classes and within the classes we have to consider mean square variation we have to calculate. Since it is a test of significance tool, we have to consider two types of hypothesis. One will be null hypothesis, hypothesis of no difference, and one will be alternative hypothesis. Okay, so if we carry forward that particular example, that we will considering that the mean effectiveness of all the different types of K ration will be equal, and alternative will be that they are not equal. Okay, we don't know which one is not equal, but they are not equal. One of them is not equal. These are some of the notations that we will be using. That is small k, we have all came across small k, that is the number of independent samples or groups. Then small ni is our number of observations in the ith sample. There is first sample will be covering n1 size, then second sample will be covering n2 size, like this way. And capital N is the sum of the total number of observation. We can say it sum of small n1, small n2, like this way. And capital Ti dot, that is the total of the ith sample. Okay. And Yij, the jth observation of the ith group. So these are different types of notations that will be used while calculating some kinds of calculation that has been that will be done in this particular ANOVA, analysis of variance test. These are some of the formulas that will be used, and there are some kind of other methods also that can be used to calculate the sums of square due to within and sums of square between. Okay, this sums of square within and this sums of square between, that will be calculated, that will be put on a certain kind of ANOVA table that will be observed in the next slide. So this all the calculation has been done to put the measured value to a certain kind of ANOVA table. That then only we can finally calculate our F test statistic, that is the variance ratio. So in this particular slide, the total variation that will be considered in this particular ANOVA, that is split into two types of variation: sums of square between groups and sums of square within groups. That I have already said in my coming slides, that this total variation will be observed and split into two types of variations: within variations and between variation. This is the form of ANOVA for one-way classified data, one-way classified, we can say, classification. So here we have 5 columns. First column is source of variation, that is variation within groups and between group has been considered. And the second is sums of square of the deviation from the mean. Okay, since mean is a stable measure of central tendency, so observation from the central tendency gives us a better idea about the variation that has been occurring. So sums of square between groups, sums of square within groups, then degrees of freedoms are there. For sums of square between groups, it is small k minus 1. Small k, we all know, there is a number of sample or number of groups that the observations will be divided. And capital N minus k, that is the total number of observation minus respective classes or respective samples. And similarly, we have already seen this mean sums of square or formula, mean sums of square. That is sums of square deviation from the mean divided by degrees of freedom. And finally, it is giving us the calculated F value. That is the most important part of this ANOVA technique. Then only we can compare it to what? Our test of significance procedure is same for both ANOVA as well as and other test of significance technique. That first we calculate the test statistic, calculate test statistic value. Then we compare with the tabulated value that is given in the tables. Certain kind of standard tables are there. So for F test statistic also we have certain kinds of F tables. Okay. So the rule is same for ANOVA also. The test statistic F follows F distribution with k minus 1 and small and capital N minus k degrees of freedom. Okay. For certain kind of in F table we have to observe the standard value for k minus 1 degrees of freedom and capital N minus k. And if the observed value of the test statistic exceed the tabulated value, we are rejecting the null hypothesis. That is, the sample means are not equal. And if the observed value comes to be greater than the tabulated value, then it is said that the sample means are equal. Okay. So this is the rule that will be followed in the test of significance. Just like other tests also, here also we will be following this rule only. So this is the ANOVA table. Sorry, not ANOVA table, F table. Standard F table, all the values are given here with respect to the degrees of freedom. We have two kinds of degrees of freedom that we have to look for. Say for one-way ANOVA, we have to look for the standard value k minus 1 and capital N minus k. Then it is, if our k minus 1 is 3 degrees of freedom and capital N minus k is our 12, then it is our standard value will be 2.61, yes. The interaction point of this row-wise degrees of freedom and column-wise degrees of freedom, where our the value cross junto amak korise, that value will be our standard value of F. So that was for 10% level of significance. On 10% level of significance, we have to reject the null hypothesis, and 90% we have to accept. And this is for 5%. Okay, 5% probability we are rejecting the null hypothesis, and 95% probability we have to accept the null hypothesis. So these are some of the problems we have considered in this particular ANOVA technique. So this was all about your one-way ANOVA. So now we are moving towards our two-way ANOVA. Now we have a, in two-way ANOVA, what we do? Two-way ANOVA, earlier we have observed that in one-way ANOVA, we divide the observations into certain kind of k classes, okay? On the basis of certain kind of one factor only, there is a different types of ration. We covered these observations into certain kind of classes, that is one-way classification. But in two-way ANOVA, we have to cover them into two classes, okay? Here we are considering factor A has some kind of h classes, small h classes, and factor B has some kind of small k classes. So total number of observation, if we consider small h as 4 and small k as 6, then our total number of observation will be 24 observations, okay? That will be our capital N. So the this slide has said that these hk observations may therefore be arranged in the form of a two-way table with h rows and small k columns. This scheme of classification according to two factor of criteria is called two-way classification, and its analysis is called two-way analysis of variance. So earlier the classification has been done on the basis of one factor only. So it was one-way ANOVA. So now the technique has been changed to two-way classification. So it is a two-way ANOVA. Here two factors will be considered. And now we are considering here the same example that has been considered in one-way ANOVA also. Here one more effect has been associated. That is the effect due to the breed and stock. So we can consider three types of effect from this two-way ANOVA. That is, first effect is due to the different types of ration. That is our that we have considered in one-way ANOVA also. And the second effect is due to the different types of breed and stock. And the third effect, that is the error effect, that will be there only within the observation, chance effect. They cannot be traced as well as identified. So here the capital N number of cows has been divided in the basis of these two types of factors, different types of ration as well as different types of breed and stock. So the mathematical model that will be considered here, there is one more effect has been associated with it. There is beta J. Beta J is considered as different types of effect due to different types of breed and stock. Okay, JH breed and stock of cows. And other effects are similar only. That is effect due to ith ration alpha I. Similarly, mu is the general mean effect. We have all came across this general mean effect. And epsilon ij is the chance effect. This is due to the effect due to the within observations. Within observation or karne junkhini amar effect khini ahibo hekini ami epsilon ij buli consider kori bine heri korim linear model to. And the notations are also same like one-way ANOVA, but here some kind of notations, some three notations has been added. That is T dot J. T dot J is the total of the jth sample, and y bar dot J is the mean of the jth sample. Okay. And other notations are same only, number of independent samples or groups. Then your capital N is the total number of observations in all the samples, like this way. Okay, now we are moving forward. So in two-way ANOVA, we have to test two types of null hypothesis here. In one-way ANOVA, we have tested only the effect due to different types of ration, k different types of ration. But here we have to consider one more factor, that is the effect due to j different types of breed and stock. Okay, that is beta. First we will be considering the null hypothesis, hypothesis of no difference. That is beta 1 is equals to beta 2, like this way up to beta j. And similarly for k different ration, we have alpha 1 equals to alpha 2 dot 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 alpha k. And this is the form of ANOVA table that we have to consider in two-way ANOVA. First, there are sources of variation due to factor A, due to factor B, as well as due to error. Okay, and sums of square due to factor A, sums of square due to factor B, and sums of square due to error. So respective degrees of freedom are also there, P minus 1, Q minus 1, and for error degrees of freedom it is P minus 1 and Q minus 1. Okay. So here we can see that we will be calculating while dealing with two-way ANOVA problems that two types of F test statistic value. First is variance ratio due to mean square error of first factor is to mean square error and second is due to mean square error of factor b divided by mean square error. Okay, so since we have considered two types of null hypothesis, that's why we have to calculate two types of f test statistic value, and this f test statistic value will give us an idea while when we will comparing with a particular standard value, that either we are rejecting the null hypothesis that has been considered in factor A, or we are accepting it, or either we are rejecting the null hypothesis that has been considered in factor B, or we are accepting it. Okay. So the rule is same only, just like 1A ANOVA, but here we have to consider two types of standard value for 2A ANOVA. That is, for factor A, we will be considering standard value p minus 1, and this is for error degrees of freedom. But what is small p and what is small q? That are the number of classes or the number of groups that the factor A will be divided, and similarly for factor B, the number of classes or number of groups that the factor B will be divided. That is small q. So this example has been considered here. Consignment is a factor A, we can say, and observer is a factor B. So consignment having how many classes? 6. Okay, and observer, there are 4 observers. So here we are considering all the consignments are equal and all the observers are equal. So we'll be calculating some kind of sums of square due to factor A, that is consignment, as well as sums of square due to factor B, that is observer. So we'll be observing other example also. So this is an example related to some kind of illness that has been caused in the virus in the city, and concerning some restaurant inspectors and some kind of restaurants. So this is the data regarding this example, that we have 5 inspectors and 3 restaurants. So we'll be observing that either the 3 restaurants are the data that has been given in ANOVA 2A classification, either they are equal, 3 restaurants, their mean effect are equal, or inspectors that are evaluating this restaurant, their evaluations, their mean effect evaluations are equal or not. So here we'll be considering 2 types of null hypothesis, for inspector as well as for restaurants. And this is the example that we are considering for certain kind of salesman and the method that has been trained in some kind of training programs related to salesmen, that is method A, method B, and method C. So the data is salesmen, there are 4 salesmen, 1, 2, 3, 4. If we consider salesman as a factor A, that our P will be, small p will be 4. And similarly methods, there are 3 methods we have to compare. Then we can compare salesmen as well as methods. So test whether there is significance difference among the methods and among the salesmen. Okay. So this was all your related to 1-way as well as 2-way ANOVA. It's a short lectures. Some important concept related to 1-way ANOVA and as well as 2-way ANOVA has been covered in this particular lecture. But there are some more problems related to this particular techniques could be practiced in coming classes. So this was all about your this 1-way as well as 2-way ANOVA lectures. So I am here concluding this particular topic today. Okay.